Android in the cloud is an enabling technology with broad applicability. Android app testing is one of the numerous use cases enabled by Android in the cloud. Android in the cloud has the flexibility of simulators or emulators while providing the efficiency of device testing. Our solution to testing Android apps is cost-effective, efficient, and enables additional capabilities not currently available to Android app testers. A sender's Android in the cloud can take a binary image from an Android phone or an image compiled from source and run it in a Linux container. Rather than using inefficient simulators or emulators, Linux container technology is used to run the apps. A complete Android system with all the services enabled runs in the container. A high-performance 64-bit ARM server can run on the order of 100 simultaneous Android images concurrently. A sender's remote graphics protocol typically uses less than 40 kbytes per second of network bandwidth while providing full resolution, low latency, lossless compression, and 60 frames per second graphics stream. The ideal cloud host for testing Android apps is ARM servers. The new generation of high-performance ARM servers are unrivaled for Android in the cloud. A large number of Android images can be tested on one ARM server. For example, approximately 100 apps can be tested concurrently on a Cavium Dual ThunderX server. With Android in the cloud, each server can test multiple apps running multiple versions of Android simultaneously. With our technology, it is easy to provide personalized Android images that have data and apps installed for individual customers. This is typically not available for testing with device farms. Every Android instance runtime has complete access to the Android API. The many processes and threads of the Android container run as processes and threads of the cloud host Linux system. Processes and threads in different Android instances are isolated in separate Linux namespaces, have resources monitored and limited by Linux cgroups, use copy-on-write file systems to efficiently create new instances of Android. The Android instances run without producing graphical output. Since pixels are not rendered, no GPU is needed in the cloud host. The graphical commands that render the GUI are compressed into a very compact data stream, which for most use cases is streamed to a remote client viewer. Current app testing frameworks run the application without GUI output, and if graphical output is needed, a few snapshots are taken during testing. With Android in the cloud, typically the complete app graphical stream is shorter than one rendered snapshot. This file can be stored with the testing results and used at any time to precisely re-render the app's graphical output, surface by surface and frame by frame. It might be inspected automatically during the testing procedure or inspected manually any time to understand if the app has been rendered correctly. A sender's technology can be employed effectively to enable the testing of Android apps. Unlike device farms, Android in the cloud provides personalized Android images that have data and apps installed for individual customers. Our enabling technology has numerous applications and may be extended to unforeseen use cases. For a better understanding of Android in the cloud, see the following video, which presents other use cases and a demo of the technology. To appreciate the full power and potential of Android in the cloud, let's talk. This presentation describes an entirely new cloud ecosystem, a cloud ecosystem with the potential to grow as large as AWS, based on modest projections detailed in the presentation. The new cloud ecosystem runs Android apps with a sender's groundbreaking enabling technology, a technology that makes running Android apps in the cloud practical and cost-effective. To fully understand the power of Android in the cloud, we will show a video demonstration. This new ecosystem closely couples cloud and mobile to create a seamless remote Android experience. Android in the cloud truly integrates the cloud-first, mobile-first paradigm to synergistic effect. We will present 3 demos. The first demo shows the functionality of Android in the cloud. In the second demo, we compare the performance of a local cloud server with a remote cloud server 4,000 kilometers away on another continent. The third shows multiple independent Android images running on one ARM server. This gives an estimate for the cost of the service. 2 enabling technologies are used to create the Android in the cloud service. A remote Android graphics protocol with very low resource usage, and an extremely efficient technique of running Android images in Linux containers. Ascender's Android in the cloud allows remote execution of unmodified Android apps. The resources used by the remote graphical protocol are insensitive to the client display pixel count. A unique and counterintuitive feature is the capability to provide high performance while running on low bandwidth, high latency, wide area networks. In addition, a large number of the existing available apps can be run in the cloud without modification. Our cloud-based technology also provides an elegant solution to security and compatibility issues of BYOD. Typically, less than 40 kilobytes per second of network bandwidth is used to provide low latency, full resolution, lossless compression with low computational complexity, and 60 frames per second graphics stream, all independent of the display resolution. This means a 4K display will use network bandwidth like a 720 pixel resolution display. Since the pixels are rendered on the client and no GPU is needed on the remote server, a very cost-effective solution is provided. We use Linux containers on a standard Linux cloud server to host multiple instances of Android images. Each container is completely isolated from other containers. Each Android instance runs independently without interaction with other instances. All data is located on the server, resulting in strong data security. Many different local clients are possible. They all work with the same version of the cloud server. We will demonstrate Android in the cloud in both private and public clouds. Either Intel or ARM servers can be used. In the demos, we use ARM servers. The local client is an x86 Intel Ubuntu machine. The local display client is an X11 program. In this system diagram, the server side is pictured on the upper part and the client side is on the lower part of the diagram, where we show some examples of use cases. Here we show Ascender's technology applied to a non-cloud use case. The Android phone functions as a normal phone. It also has the capability to provide remote graphics apps running on the phone but being rendered on the wearable device, thereby allowing us to provide Android Wear apps to devices that are not running Android. You will see 3 live demos of Ascender's remote Android technology. To set the stage, we first demo a local cloud configuration. In demo number 2, we show a real-time display of Ascender's remote Android from a distance of over 4,000 kilometers. Here we show the high quality of remote Android when coupled with limited bandwidth and large round-trip latency networks. On the third and last demo, we show how multiple instances of Ascender's remote Android can be hosted on one ARM server, a resource-efficient approach. We show how ARM servers can economically enable remote Android with cost estimates to the service provider. We will now describe our setup for the demo. We are using a standard Ubuntu laptop as our remote client, and as our local server, an Odroid XU4 a 32-bit ARM processor with a Samsung octa-core system on chip. The XU4 is in a server configuration. The only connections are power and internet. The network configuration is a gigabit Ethernet, and there is a standard ADSL connection to the internet. We will now show screen captures of the Ubuntu laptop.
Okay, we're starting up the application. RA starts it. We do RA attach. We can see that some processes are running. It takes about 15 seconds to start up this application, or the Android in the container. Normally on a phone it takes about 50 seconds, so it's over 3 times faster when you do it in a container. There are optimizations in the container you can do on the phone. When you go to the next, you click on a button, you go to the next window, you can go into the contacts. This runs the standard Google Android contact program. Has not been recompiled. It scrolls smoothly down. It'll scroll to the left. It'll scroll back to the right. We can grab the scroll bar and go down quite smoothly. Next, we'll go into the phone dialer. Standard again. We go into the dialer, push buttons as it works, and since we have no SIM card on the Odroid, it doesn't allow us to dial out. We can go into the calendar. We see everything as we expected. If we scroll up and down, we notice that the graphics work properly. Next, we'll go into the settings manager. We can go and look for applications. Here we see the applications that are on the Android instance running in the cloud. We can now try to change the launcher. We go into Home, and we'll pick the standard Android launcher. And when we go into the home screen, we see that this is the home screen of the standard Android Lollipop launcher. Is this at all practical for cloud that is not connected with a very fast network and a small round-trip latencies? The previous demos used gigabit Ethernet with a microsecond latency. When you're dealing with 10 megabit networks with 70 millisecond latencies, at least 3 orders of magnitude difference, remote graphics usually takes a big hit. Let's examine these 2 cases with the demo. One is in Paris, 4,000 kilometers away. One is local, 1 meter away. Here we see 2 windows. One is in Paris, one is local. We see very similar behavior when we scroll between the application windows. Let's go into an application we've seen previously. We can look at the contact application, for example. Left and right. Scrolling up on the right, smooth. Scrolling up on the left, smooth. Very, very similar. They react completely the same, with very small differences in latency. But in effect, you can get very similar performance between a local and an internationally connected remote Android server. The local server is on the left, and the scale-away public cloud server located in Paris is on the right. We will now demo multiple instances of Android running in different containers. Each container is isolated from all others. For this demo, we will run 4 Android images on an Odroid XU4. Here we see the 4 images, each one in its own window. The first one will run the contact list. In the second one, we'll run the standard dialer. In the third one, we see we have a different launcher, and we'll run the settings application. And in the fourth and last, we will run the calendar application. Let's see if all these applications respond. Everything scrolls smoothly. So we have 4 applications. Each one runs independently of the others, and they seem to run a reasonable response. It would be interesting to figure out how much would providing service for one customer cost. First, let's define the terms of service. We want 24/7 availability, fixed cost, and near-native performance. We can use the pricing of Scaleway's C1 ARM servers as a benchmark to price the service. A C1 server costs €2 a month. We estimate that one C1 server can support 4 Android images running in containers. This gives us a cost of 50 euro cents per month, or €6 a year.
Once we have implemented the infrastructure for Android in the cloud, multiple use cases become possible. Let's examine one scenario. Durable goods are defined as goods with long lifetimes. Google updates Android software versions annually. Android smartphones are replaced by owners on average every 2 years. Usually 2 major annual software updates for smartphones are provided, and then support is dropped. Smart TVs, however, are replaced by owners every 6 years on average, and will have the need for 6 major software updates. The task of keeping durable goods relevant over long lifetimes is daunting. An imaginary smart TV bought 6 years ago would likely be running Windows XP, not very useful today. By hosting the apps in the cloud, a future smart TV would be relevant for many years after purchase. In 2022, you should be able to access a new app on your smart TV that runs on Android 12.1 Quiche. This model will enable a long-term revenue stream years after the TV's purchase, provide long-term customer engagement, and will, of course, provide a need for a large-scale supporting ARM cloud. In 2016, approximately 150 million smart TVs were sold worldwide. If we assume 10% adoption of Android in the cloud, and assume that the remote Android cloud servers are scaled to support 25 client smart TVs comfortably, we would need 600,000 remote Android cloud servers for each year of smart TV sales to support 15 million smart TVs. This scenario assumes sales and Android in the cloud adoption volume to be flat. Thus, the combined number of cloud servers needed for steady-state support is the yearly number of cloud servers times the average lifetime of smart TVs. This gives us 3.6 million cloud servers, the approximate current estimated size of the AWS cloud. Adding a second use case, such as a smart fridge, impractical with current technology, but feasible with Android in the cloud, the number of cloud servers needed to support the smart fridge use case would be greater than those of the smart TV use case. These are just 2 of many use cases that can be supported by Android in the cloud. We believe that our technology has the potential to allow Android in the cloud servers to gain a significant share of cloud presence and to achieve the fusion of cloud and mobile technologies. To become better acquainted with the full power and potential of Android in the cloud, let's talk.